You typically calculate acceleration in terms of change in velocity divided by change in time, and usually what that amounts to is doing a calculation like this. You take some final velocity, subtract an initial velocity, and divide by some time interval. And this is a pretty straightforward calculation if you just have numerical values for velocity final and velocity initial. The problem with this is it really only works in the context of one-dimensional motion, which is usually what you start studying in physics. Eventually, you have to proceed to two- and three-dimensional motion, and you learn that acceleration is a bit more complicated. First of all, it doesn't always just result in a change in speed. Sometimes it results in a change in direction instead, and sometimes both. So the question arises, how do you quantify acceleration if it is not the speed of an object that's changing, but just the direction? So in that case, the numerical values for v final and v initial would be the same. So I'm going to go through sort of two separate derivations that I have come across for quantifying what we call centripetal acceleration, or acceleration that causes an object's direction to change. The first one I encountered, I believe, in the writings of Richard Feynman, a Nobel Prize-winning physicist, and the second one comes from a short book by James Clerk Maxwell, also a very, very famous physicist. So the arguments are actually deceptively simple and elegant. So the first one is an argument based on geometry. So let's say we have a circle with radius r, and some object is moving along that circle at a constant speed. So the velocity vector for this object might look like this at some point in time. A very short time later, the object will be at some different point along the circle, and I'm going to exaggerate the change in its position just so things are easier to see, and the velocity vector will point in a slightly different direction but should have the same length if the object is not changing speed. So we can take these two velocity vectors and kind of put them next to each other because we're really supposed to be considering a very, very short time interval. So the object has really barely moved along the circle. So these two velocity vectors will be very close together, and they'll make some small angle. And the angle that they make should be the same as the angle made between these two radius vectors. I'll just call that theta. The vector that connects the first velocity to the second one would point in this direction. That would represent delta v. So the issue here is that, or the point here, is that this triangle is going to be similar to this triangle here. So what are the other dimensions of the blue triangle? Well, the short side of the blue triangle will be the distance that this object has moved along the circle. So let's say some time interval delta t has passed. The distance along this arc we could call ds would be equal to, or I guess let's call this delta s, would be equal to the velocity multiplied by delta t. Okay, so we have two similar triangles here, so we can set up a ratio. The small side divided by the long side of one triangle should be the same as the corresponding ratio for the other. So for the blue triangle, the ratio of the small side to the long side would be v delta t divided by r, and for the red triangle, that would be delta v divided by v. So we want a measure of the acceleration, which is the ratio of the change in velocity divided by change in time. So if we rearrange this equation a little bit, we will get v squared divided by r is equal to delta v over delta t, which if the time interval becomes very, very, very small, would become a derivative dv dt. So this derivative dv dt is the magnitude of our acceleration, so that evidently is equal to this quantity here, the velocity squared divided by the radius. So this is where you get this formula for centripetal acceleration. When an object is moving in a circle at a constant speed, the magnitude of its acceleration is equal to the square of its speed divided by radius. You should convince yourself that this does have the correct units for acceleration, meters per second squared. And as far as the direction goes, the direction of the change in velocity vector here points in a direction that will be perpendicular to the velocity vector in the limit where this angle becomes very, very, very small. So it turns out that the acceleration is pointing directly towards the center of the circle, and that will always be the case when this object is moving at a constant speed. All right, so that's sort of one way of deriving this expression here. Another way I've seen is, I think, even more elegant, comes from Maxwell. He says, okay, suppose we have an object moving around a circle. We could draw a radius vector or a position vector that points to the particle as it's going around, and the velocity vector for this particle would point perpendicular to that with a magnitude that tells you something about how quickly the position is changing. So, if the radius of the circle became, twice as great, but the object still completed the circle in the same path, in the same time, the velocity vector would be twice as great. So the length of this vector is a reflection of two things, both the size of the radius, but also how quickly that radius vector is changing. And as the object goes around the circle, this radius vector will kind of sweep out a circle. It will rotate by 360 degrees. The velocity vector will also rotate by 360 degrees in the same time. So Maxwell's argument was to say, okay, let's suppose we take this velocity vector and we put that at the center of the circle. So we let it rotate with the radius vector. It will sweep out a circle similar in size. And so this velocity vector will go around, and it now sort of looks like the radius vector we had before. So if we want to find the acceleration vector should have the same relationship to the velocity as the velocity vector has to the radius, because the velocity is just the derivative of this position vector, just as the acceleration is the derivative of the velocity vector. So as this velocity vector goes around the circle, we should have a similar relationship there with the acceleration vector, meaning the acceleration vector will be perpendicular to the velocity vector, and it will have some magnitude that is a reflection of how quickly the velocity vector goes around. So his argument was that we should have a sort of geometric progression here. Whatever the ratio is between the velocity and the position vector, we should have the same ratio between the acceleration and the velocity vectors. So again, I think he had a diagram in his book where the acceleration vector and the velocity vector and the position vector were all sort of positioned at the center of the circle. And I haven't really drawn this accurately, but his argument was that this ratio v over r should be the same as the ratio a over v, which just multiply both sides by v gives you acceleration is equal to v squared over r. So this one's maybe a little more abstract than the other one, but I think is just really, really elegant, so I wanted to show that as well.